right, let's slowly start. It's a pleasure to welcome Claus Leitherer from Space Telescope Science Institute in Baltimore today as our speaker for the Heidelberg Joint Astrophysical Colloquium. Claus is actually a Heidelberg veteran. So for those who don't know, he did his diploma thesis back in 1982 at the Landessternwarte, at that time with Professor Bernhard Wolf, actually working on the B hypergiant Cygnus OB212. Still an object that we care a lot about today. 3 years later, he did his PhD also here in Heidelberg on LBVs, with the official title being the infrared energy distribution of OB stars with mass loss, together with Immo Appenzeller and also with Bernhard Wolf. Afterwards, he stayed briefly for a postdoctoral position until he got a Theodor Leinen Fellowship with the fellowship from the Alexander von Humboldt Foundation at the University of Colorado in Boulder. Then in 1988, he joined the institution that he has been ever since, namely Space Telescope Science Institute, first as an ESA staff astronomer. He then switched to the US side in 1993 as an associate astronomer, got tenure in 1999, and since 2007, he is just what one would call a full astronomer, so basically the equivalent of a professor at STSCI. So that position he has filled since 2007, so for quite some time, and in this time he has had many leading responsibilities in the scientific community inside and outside STSCI. Just to name a few, he has been chair of the IAU Working Group on Massive Stars. He has been president of the IAU Division J on Galaxies and Cosmology, and he's also the oncoming president of the Division H on the Interstellar Matter and the Local Universe. And especially maybe for the students, if you're interested, he was the previous head of the Hubble Fellowship Program. So if you're interested in applying to that, you might want to ask Claus some questions in the student meeting afterwards. And also, he's the head of science policies, so he has to do a lot with the formalities of the HST telescope time allocation. So don't beg him to give you time. But if you are considering writing a proposal, he's a very good person to ask for. So with that, we will now turn to the science part of this talk, and Claus will give us some insights about local galaxies as cosmic bridges. So please, Claus, take it away.
Thank you so much, Andreas, for this very kind introduction. I'm excited to be here, and it's more than 45 years ago that in this very auditorium, I had my first freshman class in experimental physics. And I still remember, it actually looks pretty much the same. There was the same benches, and I remember the blackboard there, and this thing was not there. But otherwise, I think it's pretty much like time travel back 45 years ago. That's what it looked like. Now, without further ado, let me first introduce to you my collaborators. We are a mix of junior and senior persons, including students, postdocs from essentially the Americas and from Europe, including, as you can see here in Heidelberg, here's one of our collaborators, Andreas. So we are a very good mix of people, and many of these persons, most of them whom you see here, were at some point actually members at Space Telescope, mostly as postdocs who then moved on to all over the world. So let's go to the science here. Does it go? No, to do it this way. Well, okay, here we go. All right. Cosmic bridges, local galaxies. What do I understand by local galaxies in the context of this talk? So for this talk, I'm thinking of local galaxies, all galaxies that are at distances beyond the local group, a few megaparsecs, out to a distance that's still covered by galaxies that are in a slow and digital sky survey, essentially up to a redshift of 0.1 or 0.2. And it's in these galaxies where we can, what I would call, do local astrophysics. We can still study the processes in great detail, which we learn about very nearby, in the Milky Way, in the Large Magellanic Cloud, and in the Small Magellanic Cloud. And we can apply our knowledge of these processes to learn about these local galaxies. And then we can dare to extrapolate what we know in these galaxies to very high redshift. hoping that we find some local counterparts and we can learn what is happening, for instance, in the area of reionization. And I want to emphasize, it works, that this is essentially a two-way process. I don't see, say, stellar astrophysics just as a mean to understand galaxies at very high redshift. It is both ways. It's both communities can learn from these processes, both the high redshift and the local community. And I'm heavily, yeah, now it's back. I'm heavily building on a large survey I'm involved with. It's classy. It's the HST COS Legacy Archive Spectroscopic Survey of Star-Forming Galaxies. It's a UV spectroscopic survey led by Daniel Berg at the University of Texas in Austin. And COS is one of the two UV spectrographs with HST, and it gives us a plethora of data in nearby local star-forming galaxies. And I wanted to show you a few examples here. So this is one of the galaxies. This is one of the COS spectra. And there are certain groups of lines that we can identify and that will tell us about the building blocks and the ingredients of these galaxies. So let's start with the stellar wind lines, which are circled here. Typical example is the carbon-4 line that tells us about the ages of the stars and the stellar content like IMF and so on and so on. Okay. Then we have also the weaker stellar lines like stellar photospheric lines that are typically seen as kind of large-scale blanketing. It's mostly iron group elements, mostly iron 4, iron 5, and I will later on show you a relatively new method to actually use these lines in order to learn about abundances, in particular in galaxies at very high redshift. Then there are directly interstellar absorption lines like this one here. This is the carbon-2 1335. And these lines tell us about the interstellar medium, about its porosity, and also about outflows from these galaxies. And later on, I will tell you how these two are closely related. Then next, we have nebular emission lines. In the previous galaxy, this was a relatively metal-rich galaxy, so the nebular emission lines were very weak. Now this one here is a relatively metal-poor galaxy. It's about a 10th solar oxygen abundance. And once you go to relatively low oxygen abundances, then you would actually see lines like, for instance, the oxygen 3 doublet, this one here, at 1663, and other lines. This is also a very important line, the 1908 carbon-3 semi-forbidden line. And finally, there's not only lines, but so we also make use of the continuum. The absolute continuum tells us about the mass, about the luminosity of these galaxies, and the slope of the continuum tells us about the reddening and the dust content. So, right. So the goals here of my talk is to show you the synergy between the results we find locally and at high redshift, always using these galaxies at intermediate distances as what I would call cosmic bridges. And there's an abundance of information, and I have to restrict this to a few core topics. And the three I want to address in this talk. The first one, this would be about stars. I will tell you about new results we learned about the stars in these galaxies. Then the next point will be about chemical evolution and chemical enrichment in these galaxies. And finally, the third point will be the outflow of matter and the escape of ionizing radiation, keeping in mind also the era of reionization in the universe. So this is the stellar part. It's part A, and so here's the line you already saw before. So this is a very typical strong line, typically the strongest line you actually see in these spectra, the carbon-4, the doublet at 1550. And now let's take a step back and look at stellar spectra. So these are individual stellar spectra from Ulysses. Ulysses is the UV legacy library of young stars as essential standard. This was an HST director's discretionary program that produced a library of spectra of O and B stars in the LMC and SMC, and also a few other local group galaxies. So this spectra, it's a treasure trove for the stellar astrophysicists to determine stellar parameters using these stellar lines, oxygen 6, nitrogen 5, silicon 4, carbon 4, nitrogen 4, and so on and so on. And then in conjunction with optical data, one can derive all the fundamental parameters, effective temperature, log G, mass, stellar radii, and so on and so on, right? All right. Of course, that's not the only purpose. So for the population of extragalactic astronomy, so they're extremely useful to serve as a spectral library. You can use these stars to essentially build a library of stars as they occur, for instance, in stellar clusters, and then synthesize an integrated spectrum and then compare it to actual observations. Now, here's an example. So in conjunction with previously obtained data, so these are results obtained by Paul Crowther in 2016. They essentially stepped a narrow slit across the center of NGC 2070, which is the ionizing cluster of 30 Doradus in the LMC. So it's a very, very center. And when you look at the spectrum of the very center, okay, so this is the 2.2, then it can essentially go to the very center, which would be R136A. So R136A is this part here, and it contributes about, well, maybe a quarter to the total UV flux here, but essentially it contributes essentially everything to this line. This is the helium-2 1640, which you see here in the integrated spectrum. Essentially all the flux comes from R136A. Why is this important? It is very important because we know that the individual stars in R136A are among the most massive individual stars known locally. So this is again a paper from Paul Crowther 15 years ago, and it shows you the derived masses of the individual stars in this cluster. So this A1, A2, A3 does not indicate that these are binaries, but these are just it's a very compact cluster, but these are individual stars that can be studied. And this shows you, let's just focus on this one here on this diagram. It's a Hertzsprung-Russell diagram, effective temperature, luminosity, and compare with evolutionary models. And you see that these stars have masses well in excess of 100 solar masses, possibly up to 500. Now, there could be binaries, they could be a little bit less massive, but clearly there are at least 1 or 200, but more likely between 300 and 400. So we know that in this integrated spectrum, there are these very, very massive stars, and they are, under all likelihood, or very likely, responsible for this 1640 helium-2 emission line. Okay? Now, let's look, okay? Here again is our spectrum we saw before, rebinned to a resolution to make it comparable to other star clusters. And the other star clusters you see here, they are now extragalactic. So they are now in galaxies within a few megaparsecs up to a redshift of 2.4. That's the sunburst cluster, and I will come back to this one later. And you can see there's this helium-2 line, which is in R136, and it's also present in these star clusters. Importantly, there's this O5 line, which requires very high temperatures, very early type stars. You see it here, maybe here not so strong, which tells you that these clusters are very, very young. Okay? Now, let's look here at one of the clusters in R125 in more detail. R125 is a blue compact dwarf galaxy at a distance of 11.5 megaparsecs. And our cluster is this thing here. It's actually the brightest cluster, more or less in the center. That's about 2.5 kiloparsecs across. Okay? It's a galaxy which has a an oxygen abundance roughly comparable to that of the LMC, but it is less luminous. So in that respect, it's probably between the LMC and the SMC. Yeah. Okay, now what we see here is the spectrum of this cluster, and I show you here an early attempt that we did 10 years ago with Aida Wofford. Okay, the black spectrum here shows you the observed spectrum, in this case with this, also one of the UV spectrographs. Okay, and the red, I don't know if you can see this, is a fit to the spectrum using population synthesis models. Now, I should say most of these absorption here that you see, they're actually they're interstellar. They have nothing to do with the star. You should actually ignore those. So what's essentially modeled here are the emission components of the stellar P-Cygni. This one, or the carbon-4. Now also carbon-4 has an interstellar component, therefore the observations are stronger. So these are actually decent fits. So this is the difference spectrum, and you know there are some differences, but there is one spectacular failure, and this is the 1640 line. So this one essentially is not present in the population synthesis models, but it's essentially the strongest line in the spectrum. And as you can see, it's really a spectacular failure. So what would we actually say about this model? Well, yeah, doesn't work. Now, fast forward. Okay, 10 years later. So here we are again. So this is again Aida leading this effort. Okay, again the same cluster, and now fit to the spectrum: nitrogen-4, helium-2, carbon-4. Okay. Nitrogen-5. There's oxygen-5. Certainly not a good fit, but at least there's something. So what's the difference? The difference is now here. Now this includes these massive stars, the 300 solar mass stars, which we know are actually there, but we did not include at that time because we thought 10 years ago that this would have been less massive, but more evolved Wolf-Rayet stars. But now we have these relatively young, essentially O-type stars, which are just massive. They're not particularly hot. They are hot, but not excessively hot. They're early type O stars that are very, very, very luminous. Yeah. So this makes the difference. And so what are these beasts? So this is a Hertzsprung-Russell diagram, which shows you the WN stars observed and analyzed in the large Magellanic Clouds, mostly essentially by the Potsdam group. And you see here two groups of WN stars. Yeah. Essentially those here, which are in this regime, which we would call the classical WN stars, which are really Wolf-Rayet stars, the evolved descendants of O stars. And these are the ones which I would call, basically hidden Wolf-Rayets. They are not really Wolf-Rayet stars. So these are just very massive stars, still hydrogen-rich. And these are the ones which we would call the very massive stars. And that's what we are all very interested in, including Andreas. That's our main collaboration here. And I want to show you, because sometimes also a figure from one of Andreas' papers, but because sometimes there's a suggestion that these very massive stars are also a very significant source of ionization. And this shows you the SED of two examples. I just first want to explain the SED. There are two regions. This is the non-ionizing ultraviolet up to 912 angstroms. This is the ionizing flux, basically the Lyman continuum. This is the neutral helium continuum, and then down to from 2 to 8 angstroms, the ionized helium continuum. And you see two stars here. The one to the left would be a very luminous O star. So it has a luminosity of about 10 to the 6 or so. And this one would be more like this very massive star. So it's close to 10 to the 7. Now it has more hydrogen ionizing photons. But what happens, because the winds are so optically thick in the ionized helium continuum, so helium actually recombines. And so it's just these stars where you would expect them to be significant sources of ionization in the hard part of the spectrum. They actually emit essentially nothing. They're essentially opaque in this region. So if you read somewhere that, oh, these stars, these are basically the sources of free ionization in high redshift galaxies. So these are not the right stars, definitely not those. Yeah? And so this concludes the first part of my talk. And I will warn you, I will not have any summary of takeaway points in my last slide, because I know 1 hour later, nobody remembers those anyway. So what I want to do is after each of these 3 sections, I have 1 takeaway point, which I want you to remember. Okay, so part A. This one I want you to remember. There's strong evidence for the existence of very massive stars with masses of several hundred solar masses, both as individual stars and in unresolved star-forming regions of galaxies. Okay, and with this, I move to part B. And this is mostly about chemistry and chemical enrichment and chemical evolution. So now I want to point you to, again, using the classic spectrum, to a region where you see hardly any lines, but in fact there are lines. There are many, many faint lines. So this is the blanketing mostly of iron lines. Why are we so interested in iron? So iron probably is the most important isotope element when it comes to chemical evolution. It's the anchor point for essentially all chemical evolution models of galaxies. In fact, the relation between alpha elements in iron versus the iron abundance in a galaxy has been recognized as early as 1962 by George Wallerstein as one of the most important diagrams in galactic chemical evolution. So now, if you talk to somebody from the late type star or early type galaxy community, they would say, well, yeah, it's trivial. Everybody derives iron abundances, but not so when it comes to star-forming galaxies and also to hot stars. Okay, that's just the opposite. And why is this so? Well, this is a diagram Rolf Kudrycki always liked to show to convince everybody that iron is complicated, and he succeeded. I think everybody agreed. So if you look at this protein diagram, you know, iron 5 is a very, very rich spectrum. So lots of challenges, both in terms of laboratory astrophysics, atomic data, and of course, non-LTE effects, and so on and so on. So we would love to basically predict any of these tiny iron 4, 5 lines, but we are just not there. It's just not possible to do this individually for these lines. So typically, iron abundances for individual O stars are very hard to come by. Now, you could say, well, then you go to the interstellar medium, because massive stars are essentially coming right fresh from the interstellar medium. So determine iron abundances in the interstellar medium. Then you have the iron abundance by default from the stars. But of course, iron is sitting on dust grains. It's heavily depleted, it condenses there. It's very hard to get the gas phase abundance of iron. You know, it can be, some try it, but it has huge correction factors. So it's very, very uncertain. In fact, it's even more difficult because the depletion in strongly star-forming galaxies is actually time variable, because the dust grains can get destroyed by supernova explosions, and therefore the lines actually that you measure are actually variable depending on the explosion of core collapse supernovae. So basically, we have really no reliable gas-phase iron abundances. So what to do? Now, coming back to the line blanketing. Now, when I said we cannot get abundances for these individual iron lines, we can actually look at them as an ensemble. So these are synthetic spectra from Starburst 99. And for just the standard population, it shows you the UV spectra going from twice solar up to about a 20th solar. And you clearly see that the blanketing has a trend, clear trend with metallicity, with the iron abundance. And what you see here, the gray is the original one, and then the blue one is basically binning it to lower resolution for comparison with actual galaxies. Okay, and so the idea there is basically to do this, to use these spectra and use the strength of the overall blanketing as an indicator of the iron abundance in galaxies. And this is now something which is becoming more and more common. Okay, so this is relatively complicated, so please bear with me. I didn't make this plot, but so let's just focus on a small region here in this region, and let's zoom in here. So these are Lyman break galaxy spectra, essentially star-forming galaxy at redshifts around 2 to 3, around cosmic noon. And the spectrum here is a composite of 30 such star-forming galaxies. And the observations is the black line, which you may see somewhere here, right? Okay. And so what they did now, they compared this to different Starburst 99 models with different metallicities. So 0.08, this would be LMC, this would be more like the about a little less than the SMC, and this is very metal poor. And then just, by comparing the blanketing between the observations and the data, then you would say, well, the one with 0.08 clearly is too strong. The 0.001, well, I think that's a little bit too extreme. So basically, the truth is probably between the two. And when you use this technique, that you find that about a metallicity, in this case, an iron abundance of about 1/10 is probably a good match. Then at the same time, you take the nebular emission lines, which in this case, because of the redshift, would be in the observed frame in the H and K band. And then you do a standard nebula analysis, and you derive the oxygen abundance. And the oxygen abundance is only half so. So what you find actually that the iron abundance is actually 5 times lower than the oxygen. So it's highly enriched in oxygen. You can do the same game. So this is a different example, and I'll do this quickly again. So this is the ultraviolet spectrum, and this is of course redshifted to the optical. And so this is the optical spectrum, which is redshifted to the near infrared. You can do the same game, and you find about the same result. That the iron group elements are underabundant by a factor of 5 or so. And just to summarize this, so this is again from a very recent paper by the group in Edinburgh, where they derived the mass metallicity relation for the stars and for the gas in a large sample of galaxies at a redshift of 3. And so what's plotted here is the stellar mass for a sample of galaxies, where it was derived from the UV luminosity, versus Z, where Z means the oxygen abundance for the gas, or the iron abundance for the stars. So this is the relation for the iron, and this is the relation for oxygen, which is typically a factor of 3 to 5 higher. Yeah? Now, I should say, actually, as a caveat, that the nebular abundances are derived what's called the strong line method. It's essentially an indirect calibration, but that can be easily remedied with JWST, because all these galaxies that have been observed from the ground in the infrared, they're easily accessible with JWST in a very short time. So these abundances may become, the error bars may become much, much smaller, and in particular, systematics may go away. Yeah. Now, can we also learn something from the stellar wind line about the enrichment? And so this is from a paper that has been led by Elise Clark, who was our undergraduate team member at that time. So this was her undergraduate project. And in the meantime, now she's a graduate student, second-year graduate student at University of California, San Diego. And what Elise did, she looked at the behavior of the carbon-4 1550 line in a sample of 29 star-forming galaxies. And they were observed with IOE. IOE was a satellite operating in the 1980s, small satellite. Why did we do this? Because the quality of this spectra is worse, but it's very comparable, or even better than the spectra we can observe at very high redshift in the area of reionization. We want to see what can you actually do with the spectra. And so we measured the equivalent both for the emission and the absorption component of carbon-4. And positive values just mean now that it's strongly in absorption, which is essentially always the case. It's much stronger. The absorption component is much stronger. And it's compared here to it's a Starburst 99 model. So this is the prediction for the run with oxygen abundance. So this oxygen abundance, and this is the equivalent width of the 1550 doublet. And there are very few free parameters. It's an equivalent width. There's really very little you can do. And you see the model predicts that at very high metallicity, it's strong, and then it basically asymptotically goes to zero because there are no more stellar winds, and there's then just naked continuum. Now, observationally, you see that there is a breakpoint here around an oxygen abundance of 8.0. So this is essentially where the stellar wind lines become so strong that they're overwhelmed, overpowered by nebular emission. So here, the equivalent width becomes negative. This means here, actually, you don't have any more stellar lines, but you have a narrow nebular emission line. Now, obviously, this would no longer agree with the stellar models because this is a pure nebular line. Okay? But overall, this is very nice agreement. Now you would say, well, sure, it scales with oxygen abundance, but what's the big deal? Now there is a big deal actually. Keep in mind what you actually measure in terms of abundance with the carbon-4 line is not predominantly carbon, because what you measure is actually the wind strength, and the winds are driven by iron lines. So the strength of the carbon line depends actually on iron. Okay? So indirectly, you're measuring an iron abundance. And so these models were run with a solar iron or alpha element over iron ratio. Okay? And they only agree, most likely, because both the models and the observations are for solar. So in these galaxies, there's no indication that the star formation activity was so strong that it resulted in a significant enrichment of oxygen in the interstellar medium. And so Andreas and I, we want to pursue this method to actually run grids of models to use this actually as another method possibly to derive iron abundances in galaxies that is otherwise not accessible. Okay, I'll say a few words about nitrogen enrichment, because this has become very important now in the context of galaxies at very high redshift at the era of reionization. So locally, there's very little evidence that massive stars, in particular Wolf-Rayet stars, lead to significant enrichment of nitrogen. There are a few examples. So this is one. This is a blue compact dwarf galaxy. It's NGC 4670. And so this results from integral field spectroscopy. So this is a 3 by 5 arcsecond field. And this shows you the flux in the broad Wolf-Rayet blue bump. Essentially, what you see here is the surface density of Wolf-Rayet stars, of W and L stars. Okay? So that's where they are. So they're concentrated here. Now, this one here is a nebula analysis. It's essentially the same size here. And in this case, it's the ratio of nitrogen over oxygen. So this is in the surrounding interstellar medium. It's the same field, and you see around the Wolf-Rayet stars. Now, the nebular nitrogen is actually enriched relative to oxygen, and so the interpretation is, well, so there are several hundred Wolf-Rayet stars, and they enhance the nitrogen in the interstellar medium. Now, this is not generally true in the local universe. So there are quite a few studies, and there we go. And this is, it has been long known, it has been known for a long time that Wolf-Rayet galaxies containing Wolf-Rayet stars, are not significantly enriched in nitrogen. So there are two samples. The open dots are galaxies with no indication of Wolf-Rayet stars. The full dots here are Wolf-Rayet galaxies. And there's no significant difference in the N over O between those two populations. And this has been known for quite some time. So so our galaxies in the local universe, they're still relatively normal in comparison with these very extreme starbursts. Okay, now let's go higher out. So this is the famous sunburst arc. It's a galaxy that's multiply lensed. It's a redshift of Z of 2.4. It's, as you can see, it's a beautiful example. So this is probably the only slide I have, but it'd be nice if it were a little bit darker. It's a very, very rich cluster. You see actually many, many arcs, and maybe you can see this, but there are many, many dots here on the arc. So this is all one and the same star cluster, which is multiply lensed here. And you get an exquisite spectrum actually of extreme fidelity, which is actually better than what you can get in the local universe. And there you can actually do analysis, in this case, a direct analysis of N over O. And yep. And again, I want you to focus only on the top, which shows you basically the axis is here. It's the oxygen abundance. The solar value would be here. That's the vertical line here. And over here is N over O. This is the solar value here. Okay, and this is the value that's measured here in this cluster. And I should say, for those of you who are not so familiar with chemical evolution, N over O shows a very distinct pattern. So the ratio is constant, where what we call nitrogen is the primary element, and then around 8 or so, then it rises, where we say it becomes a secondary element, meaning its abundance depends on the prior abundance of the element because it's processed in the stars. So when you compare N over O, you have to compare it with this sample. You should not compare it with the sun. And you see that it's overabundant by a factor of many. And in this case, the interpretation is that it's a cluster of 700 WN stars, and they're responsible for the enrichment. But in this case, most likely, these tend to be these very massive stars, probably formed in a very dense cluster, and that really have very strong stellar winds and release the nitrogen in this cluster. At least that's the preferred interpretation here. Yeah. Oops. Yeah. Right. And why did I show this? Okay, now let's do a further step. Now we go from a redshift of, actually I said 2.7, should have been 2.4. Now let's go to redshift 11. Universe at that time has an age of a little more than 400 million years. This is a very famous galaxy which came out of the initial surveys with JWST. There are zillions of papers. You know, everybody wanted to be the first. So it's GNZ11 stands for Good North Z redshift of 11. And again, so here there was an analysis of the nitrogen abundance. And in this case, it's even much, much more extreme. So the interpretation here is that it lives in this regime here, even much more extreme. And again, so the suggestion here is that these are very massive stars that form actually because it's a very dense cluster. There's mass segregation, and massive stars move to the center of the cluster. Some of them merge their interactions, and you get these very massive stars, and they release the nitrogen. Needless to say that this is somewhat uncertain. Also, the analysis is somewhat unusual. So it was done by the nitrogen 1750 and the 1486, which is a very unusual way to do this, and was basically done by comparing this to other galaxies. But you know, you do what you can do at a redshift of 11 or 12. Yeah. And okay, so this was my part B. What I want you to remember is that the ISM of extreme star-forming galaxies at intermediate and high redshift exhibits evidence of rapid chemical enrichment over timescales of a few years, maybe in the case of these Vauquerets stars, up to hundreds of millions of years. These were the O stars, where the gas phase and the stellar iron abundance was different. Which brings me to the third part, which is about outflow of matter and the escape of ionizing radiation. Again, here's our good classic spectrum. And so now let's have a look at a line, an interstellar absorption line, like the silicon 2, and there's also sulfur 2 at 1260. And in the next slide, we see this at a larger higher magnification. That's by a paper from one of our classy members. It's the Zhu et al., who studied galactic outflows in a sample of our classic survey. And so they fitted this. So essentially, there are two components. So there's a static component, which is essentially the inner interstellar medium, and then there's an outflow component. And in this case, you have a velocity of the order of a few hundred kilometers per second outflow. For the whole sample, the mean was about 190 kilometers per second. So what can we learn with this? So now here's a plot of all the galaxies, and plotted here is the circular velocity, which is essentially a proxy for stellar mass, which is plotted here. There's the stellar mass. You see their masses, some of them are actually very massive, and we go down to about 10 to the 6. Okay, and this is the mass loading factor, which is essentially the mass loss rate in the outflow divided by the star formation rate. Essentially, this tells you how efficiently the outflow removes the gas from the galaxy relative to the star formation. And so what you learn from this figure is that at low masses, outflows remove more than 10 times more gas than what the galaxies would actually form into stars. Yeah? Yeah? Now, this was just about the mass, but what about the chemistry? Then you can go one step further. What about the elements? And this was a paper we did a few years ago with John Chisholm, but we'll repeat this with the whole classy sample. So what's plotted here is the outflow metallicity, and metallicity essentially means now so elements measured in the nebular gas. That's what I mean by that: oxygen, silicon, actually no absorption lines measured in the outflow. It's silicon, sulfur, and so on and so on. Again, versus stellar mass. And you can see actually that at low stellar mass, the outflows are much more enriched. Now we combine this now with the mass that's actually lost. We combine this with the mass loading factor. And you can see that so again, what we plot here is the ratio of the metals removed by the outflows to the metals locked into stars. Before that, we were just looking at the mass. Now we look actually at the metals. Okay? And so these are essentially models that actually predict what this relation should look like. These are models for galactic infall and outflow. So you model that pristine material is falling into the gas, which has essentially is not enriched, and the galaxies lose mass with these outflows. And the interpretation, the most likely interpretation, is that at high mass, most of the material that's in the outflow is actually interstellar material that's just entrained in the outflow, whereas at low masses, it's mostly the material, the oxygen, and so on, that process that comes from a supernova. So there's a higher fraction of the newly generated elements. Okay? And so these relations are actually responsible for the observed mass metallicity relation. So most of you probably have seen this fundamental relation many times. So this was from a paper with thousands of citations by Christy Tremonti. This was part of her PhD thesis at Johns Hopkins 20 years ago. And it shows you the relation between stellar mass and oxygen abundance for galaxies at redshift of about 0.1. So these are all galaxies in the Sloan digital sky survey. And you clearly say actually that the less massive stars, the dwarf galaxies, several times, 5 times more metal depleted than L stars, for the reasons I just pointed out in the previous view graph. So we think what we see there, that's the reason why we see this relation. And by the way, so this relation looks different at different redshifts, different relations. So the shape remains the same, but obviously the absolute numbers change. All right. So now I make the transition from outflows from the kinematics to the escape of ionizing radiation. Now there are many lines that we see where we see outflows, but it's not only absorption lines where you essentially look down the barrel, but it's also emission lines where we see outflow. Yeah? So one example is the magnesium-2 doublet at 2796 and 2803. Yeah. And this line is also very useful for probing the escape of ionizing radiation. Okay? So the outflows that we observe are actually highly porous. Some of them are just optically thin. Otherwise, they have essentially holes, like in the picket fence model, or are just asymmetric. Okay? Now we can use actually just pure atomic physics, the strength of those two lines, to measure the optical depth in these lines. Ideally, they would have a ratio of 2 if you're optically thick, okay? And if everything is if they're optically thin, and if they become optically thick, then the strength of the 2 would be the same, and they go to 1. Okay? And you can actually use this just analytically to basically convert this to an optical depth in these lines. Okay? And then with some assumptions on the ionization state and the absolute abundance, you can convert this also to basically a column density of neutral hydrogen, and then you can actually calculate and predict what is the fraction of hydrogen ionizing photons that get stuck in neutral hydrogen and which one would actually escape. And then you can compare this actually to measurements where you actually measured the escape fraction, where you directly detected this short wave of 912. And you see that's plotted here. Here's the predicted escape fraction from the magnesium-2 line. And here is the actual escape fraction. And you know, there's a good correlation. It doesn't work always, but it's at least it's one of the indicators, which is actually very frequently used. Okay? So why are we actually interested in this? And this is one of the big questions in cosmology and observational cosmology, namely, what are the sources of cosmic reionization? And currently, there are two main contenders. It's star-forming galaxies versus AGN. And if it's star-forming galaxies, then it comes down to the question, what is the fraction of ionizing photons that are produced that can actually leak out? Because it's clear that there are O stars, massive stars, so the photons are produced in star-forming galaxies, right? The question is, how do they get out? But they all have circumgalactic material, they have an ISM, and hydrogen is actually very, very effective in absorbing those ionizing photons. As we know, there are H2 regions, and they have beautiful recombination lines because it captures all the ionizing photons. Just as a reminder, you already reached an optical depth of 1 for neutral hydrogen at a column density of 10 to the 17, and is much, much lower than any typical hydrogen column that you observe around galaxies. Okay? So what we need to do empirically, we need to determine the escape fraction. So this sounds like a very trivial thing, right? So you say, well, let's just go to these high redshift galaxies. Let's just measure. So these galaxies are redshifted, so the Lyman continuum should be free, not blocked by the Milky Way. But of course, it's not so easy, because if you go to redshifts of already more than 3 or 4, so then the IGM becomes opaque to the Lyman continuum, because you're picking up so much neutral hydrogen that essentially all your radiation, even if it left the galaxies, would never reach us on Earth. So the only viable strategy is basically we take local galaxies as training sets. Essentially, we try to find local galaxies that actually have escaping radiation, and then we just determine, well, what is so special about these galaxies? Because not all local galaxies, very few actually, have escaping Lyman continuum radiation. So what's so special about these galaxies? Okay, and then we try to parameterize the photon escape fractions in terms of these accessible observables, like strength of emission line ratios, and so on and so on. And then we compare the properties of this local sample to those that we observe at high redshift. And then, well, we make a prediction, you know, together then with some luminosity function, how frequent are these galaxies. And then we would predict, well, can these galaxies really do the job? Can they re-ionize the universe? Okay. And this was one of the relatively early attempts. And what we did here, we used the cosmic origin spectrograph, okay, to observe a galaxy from 2000 down to 912, and this is just the end at short wavelengths. So we essentially fit a population synthesis models, which I'm not showing here, and then we predict what should be what should be the Lyman continuum if 100% of the photons escape, and this would be here. So then the continuum level would be here. In reality, it's much lower. It's here. It's not zero. There's something, but it's much, much lower. So in this case, it's just a few percent. So this was one early attempt, and this was essentially, well, essentially like a heroic effort, because it was very, very hard, because this was a galaxy that was at relatively low redshift, and you get only about 35 angstroms of the Lyman continuum. The reason is, of course, everything else would be essentially absorbed by the Milky Way. So we are only out of the Milky Way absorption by 35 angstroms. Now, a better approach would be to go higher redshift. And this is just a schematic which shows you the traits. If you do these observations at very low redshift, at a redshift of, say, 0.2, 0.3, and a redshift of 3. And you know what you have to consider is basically the information you have, the solid angle, observational challenge, and so on and so on. And I don't have time to go over this in detail, but I want to make the point. So nowadays, actually, we find the sweet point is actually doing this around redshift 0.2 and 0.3. And this is essentially driven by instrumental limitations, because you can show once you reach this redshift, then your galaxy is redshifted into a much more sensitive part of the spectrograph. So essentially, it's only COS, the cosmic origin spectrograph of HST, that can do this. And essentially, once you go to wavelengths longer than 1050 angstroms, so if you redshift the galaxies, then there's a huge gain in sensitivity by 2 orders of magnitude. So that's why you want to go to a redshift of 0.2 and 0.3. Yeah? And once you do that, so there are many galaxies now. So this was from a very large survey with COS by Sophie Fleury. Where's she? I think she forgot where she was, in which institute. I think she is, oh, she's in UMass. Yeah. So what they detected was 35 Lyman continuum emitters. And so what's plotted here is the redshift of these galaxies, the detections. And this is the flux. Yeah? So there are non-detections. There are lots of non-detections here. And this is a selection effect. This is essentially what I told you. It's actually easier to detect something at something higher redshift, because here the Lyman continuum would still be in a region of the detector that is less sensitive. So that's why there's a gap. So this is purely driven by the detector sensitivity. Okay? Now, if you put this all together, I think I'm good with time. So here's a summary diagram, but don't despair. So we don't look at all these figures. So essentially, what's plotted here is as the vertical axis is the observed escape fraction. This would be 100%, 1. This would be 10%. This would be 1%. Okay? And this is plotted against various galaxy properties. So what I want you to just look at the point clouds where you see certain trends and where you see a cloud. Clearly, in some cases, you see trends. In others, you just see clouds. Or in others, you see the cloud being condensed in some area of the few graphs. And I want to just go to 5 of them and to show you what the issues are. Yeah, so let's first look at the plot where the escape fractions are plotted versus the escape fractions or the strength of Lyman alpha. So Lyman alpha behaves very similarly because also the Lyman alpha photons have a hard time getting out of the circumstellar medium. And there's a clear trend, so which tells you, because Lyman alpha really depends on the morphology of the outflow, and obviously on the opacity. So clearly, it tells you that the morphology must play a major role in the escape of Lyman continuum photons. So for instance, if the ISM has been disturbed or essentially removed by a very strong starburst, that is very helpful for the escape of the Lyman continuum radiation, the escape. Then let's look at the dust content. That's maybe a little bit trivial. So clearly, relatively dust-free galaxies, they are more likely to have a high escape fraction. So we can actually skip this one. Okay, so this one actually, that's an interesting one. So this is essentially the hardness of the spectrum. So if the galaxies have for instance, very high oxygen 3 over oxygen 2 ratio, essentially a very high ionization parameter. In this case, also the escape fractions are high. This is actually something we observe in the high redshift universe. All these galaxies have very, very high radiation. Yeah. Another one, stellar mass. So the typical galaxies that leak radiation are not the massive ones. Okay? So it's typically the lower mass galaxies, the dwarfish galaxies. They are closer to very massive clusters. They are more likely actually to leak the radiation. And finally, I think that's the most important one. It's the star formation density. So these are the galaxies with the highest density, where the starburst is concentrated in a very, very dense small cluster. So these are the ones actually that leak the radiation. So this is the lesson we learned here. Yeah? And so just to summarize this, I think that one of these, so these are the common properties. Keep in mind, a single property is not a good predictor of the escape, but taken together, actually, you have a good chance that you actually catch a significant Lyman continuum leak. And these are basically the criteria that we apply, and then what we compare them with at high redshift. All right, and I'm almost done. Yep. And so here I show you a very recent example of what we think is a Lyman continuum leaker. So I did this talk about 3 weeks ago, and I wanted to say this is at this point the highest redshift star-forming galaxies that is confirmed spectroscopically, the redshift of 12.3. Unfortunately, in the meantime, 2 weeks ago, there's another one. Now we are at redshift of 14. So I didn't update my talk. So keep in mind. So this is okay. So this is the runner-up now. So this time the redshift had the universe had a redshift age of 360 million years, and so that's all you can do at this redshift. This is a prism spectrum. So it has the resolution here. This is about 20, becomes much larger, but of course then you don't detect any more flux here. That's more like 200 or so. It's with near spec, and so here's basically the Lyman break, Lyman alpha. Then there's the nitrogen 4 line, which again suggests that there's a strong nitrogen enrichment. Nitrogen 3, well, yeah. There's possibly helium 2, and there's also, yeah, it's probably there. There's, they say there's weak neon 5, possibly it's there, but the absence is actually in the paper used as an absence of an AGN, and the idea here is that this is really massive stars, really 10 to the 4, even 10 to the 5, basically forming within 1 parsec. So this is one of these very, very massive and compact clusters, which we think would be responsible for reionization. And yeah, almost done. So this is my top takeaway for part C. Extreme star-forming galaxies have strong winds and leak ionizing radiation, regulating their evolution and the circum and intergalactic medium. And I think there's one more. Yeah, so we did the full circle here. So now back to the beginning. I hope I could convince you that these local galaxies are useful cosmic bridges that let us see the forest for the trees. So here are our local galaxies. You still see the forest, but you can also identify individual trees, and then you can make comparisons with the tree you have in your backyard, right? Which you can see also in the middle, and then you can actually dare to make comparison to high redshift, what these forests would look like, you know, of course, with the caveat, so that the forest in the middle would probably be on the Königstuhl, right? Whereas, you know, that it would definitely be different from the rainforest in the Amazon in Brazil. But, you know, that's what you have to live with. And this was my last slide, and I thank you for attention.
Thank you very much, Klaus. That's a great overview of some really important questions. Thank you so much. I think we will ask for questions from the floor. Are there students who would like to kick off the questions? I don't see anybody. Well, non-students then? Still thinking about it. Ralph?
Thanks, Klaus, for this very detailed overview of, you know, the different scales and what we can learn from these studies. I'm wondering this role of dust and the uncertainties involved in the dust mode, so forth. Is this one of the major sources of certainty in particular? Or how would you?
Yeah, this is certainly a concern. So when I say we learn about the dust, of course, you know, also in the population synthesis models, we de-retin with the dust, but it's a very simple foreground model, like a picket fence model, what we use. So we do not account for the dust. So we do, for instance, we do not model infrared luminous galaxies or the very luminous galaxies, and being aware that a significant fraction of the star formation earlier than cosmic noon is actually hidden in very dusty galaxies. Those we don't do. Now, if you're interested at very high redshift, so there's now evidence for dust, and we discussed this this afternoon. Out to a redshift, I would say that the highest redshift now is redshift 10 or so, where there's evidence for dust. Now, in this even more distant galaxies, there's no evidence. Now, basically, no evidence means that there is no dust. At least there's no evidence, but there could be dust. But certainly, the spectra do not look like that there's a significant amount of dust. And so they're very, very blue, right? So they're as blue as can be from the perspective of stellar population models. So essentially, in the ultraviolet, you're essentially in a pure Rayleigh Jeans tail, and it's as blue as it can get.
Okay, interesting. Well, let's hope there are some galaxies that don't have dust to obscure things at the very highest redshift. It's bad enough of a headache in the local universe. More questions, please. If I may have a question, I'm interested in, you mentioned right at the end about the escape of the ionizing photons, and you sort of intimated that, you know, if you have a very local, concentrated, large star cluster, then those are the situations where you actually get efficient escape.
Yeah.
I mean, do we have any idea yet about how the typical masses of star clusters might be evolving, if at all, with redshift independently of galaxy mass? For example, I mean, if you have a high redshift galaxy with a certain galaxy mass, you have a low redshift galaxy at the same galaxy mass. Obviously, the medium and the high redshift galaxy is very, very different. So possibly the properties of the star clusters are different. Is there any observational for that sort of thing?
Of course, I showed this one example of the strongly lensed galaxies, but there are other examples. And there you also see individual star clusters like you see in the local universe. They are there, actually, right? So it's not qualitatively different. And so for these galaxies, there are analysis of the masses, and it's typically between 2 times 10 to the 6 and down to the detection limit. So it's the detection limit. So it's actually not so different from the local universe. So I would say the highest redshift where this was done was about redshift of 3 or so. So we wouldn't know at Now, of course, those galaxies at the very high redshift, at redshift 12 or so, this is essentially like a massive cluster, like 10 to the 7 solar masses or so,
Yeah,
right?
they
So
are.
these are
They are
basically-
clusters.
These are galaxies forming, right? So,
Yeah.
yeah.
Very interesting. Okay, so Elie Bastien.
Very simple question. Not
So
at
these
the
are
front,
usually the
not-
most difficult ones.
not at the front. Where do the non-escaping Lyman continuum photons go? To Balmer continuum, to longer wavelengths, Paschen
Yeah,
continuum?
well, you know,
Balmer
you have
lines?
yeah, exactly. You have H2 regions and everything, H
Ah.
alpha emission, Paschen series, everything. Yeah,
Okay.
they just stay there, right? Yeah. So you know, it's like in our galaxy or in the LMC or so, they just stay there. You can do your photon counting, and usually you find there's good agreement that the number of photons that are generated by the O stars, you would count the O stars, then you can predict what the number of ionizing photons are. And you know, within a factor of 2, that essentially agrees with what you would expect from the recombination, right?
Okay, well, don't see any more questions and they're not online, so I think we're going to wrap up now.
You wanted to show? Yeah. Yeah, I have them. So,
Okay, I have just 3 announcements.
yeah, but they are now.
Uh,
So how
which-
should I get?
Uh,
Then have to see my.
maybe it's
desktop.
not possible.
No, it should be.
Yep.
Let me. Like. How do I see? Oh, okay.
Just put them up on the screen.
Uh, This.
Excellent, excellent.
Well,
So
okay, hold on. But
uh,
then
share the
still have the
screen.
not yet excellent.
That's it. No, bad luck.
It's there.
Well, the Zoom audience can see this. I think if we strain our eyes, we can see it on the
Hold on.
side screen. So I'd just like to repeat, especially to everybody on the Zoom, but also in here, that we have a deadline of tomorrow for everybody in Heidelberg to send in their suggestions for speakers for the colloquium in the winter semester. So please contact your institute representatives at those email addresses and send in your suggestions. And then next one is, what's the next one? Oh, next one is next week's talk, which will be by Catherine Zucker from CFA in Harvard. And we're going to be really changing the scale, looking at star formation within the Milky Way and also right in the solar neighborhood, talking about all the interesting things going on associated with the bubble around the sun. And so we can look forward to that, the last colloquium of the series next week. And the last announcement is that I'd like to sort of ask Cormac Larkin maybe to say a few words about that.
Sure. So thanks to the Dr. Vanden Convent, we've got some funding for some pizza and board games this evening for the PhDs. An email went around to sign up, but if you didn't sign up, you can still join. And this will follow directly after the students' meeting with Klaus, which we will go to right away from here. So follow me to board games and pizza and discussion with Klaus if you're interested. And this is also open to master students and early postdocs. So feel free to join. All are welcome.
Yeah, and later on at 7:30, anybody who wants to can join us for dinner with Klaus at Los Primos, Neugasse 21. So it just remains for us now to thank again Klaus for this extremely clear and informative talk. And we're very happy to see HCHT still producing such great information from the local university in the UV. It's a really important part of the puzzle. Thank you very much, Klaus.